Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on inside as we jump into section 5.3 in the Big Ideas Math Integrated Math 1 textbook, solving systems of linear equations by elimination. Now, we did the substitution method in section 5.2, which was an algebraic method, so will be elimination. And for many people, it's a preferential one, but it all depends on the format, how things are set up. My guess is elimination was really convenient for us to get, at least in that form, get a variable by itself if it wasn't already by itself. And elimination will probably be set up in the way you'd want it to. In this case, no slope-intercept form setups really, but probably a lot of standard form. We'll see how it goes, but they'll show you how it goes as well. If you want to jump to the description section down below, you can download the PDF of this textbook stuff. Probably nothing to graph, so no graph paper as I'm aware of, and the problem sets is up to 35, just like the substitution version. Without further ado, let's go ahead and get started. We are going to solve systems by using elimination and solve real-life problems, etc. So same stuff as substitution. There's a previous term used called coefficient. Coefficient is the number multiplied in front of a variable, and that's an important term to be talking about for this set. To use elimination, what you're going to do, basically, well, here, I'm going to show you a version of where something is. Like, look at these two equations right here. They actually almost look identical, but they're not. They have an equation right here, an equation right here. Notice how they are lined up. The x's are lined up, the y's are lined up, the constants are lined up, and the equal signs are lined up. Lined up in such a way that things are on the left side of the equation, things are on the right side of the equation. This is ideally something that you want. Now, our goal will be to eliminate a variable. If you recall in substitution, we replaced a variable with an expression that contained the other variable. Like if y equaled something, then we could replace that expression that had an x in it for y in the other equation, and you had an equation with only x's. Our goal here will also be to get rid of a variable, such as in this case it'll kind of be y, eliminate the y's here to have an equation with only x's, and it will be simply by adding down your lists. So here's what we're going to do. If necessary, we're going to multiply one or both equations by a constant, some number, multiply both sides by 4, or divide. I'll do some division probably, depending on the questions. So at least one pair of like terms has the same or opposite coefficients. I'm going to go ahead and use opposite coefficients only. What I mean by that is if I have a positive 2y, then here I have a negative 2y. Now it's possible to use this 3x, positive 3x, and eliminate them, but then it requires subtraction. And I'm probably going to say it more than once. Trust me, people tend to mess up if you use subtraction here because now you have to subtract a negative here. And remember that things use subtraction. But if I use addition with opposite signs, adding a negative becomes subtraction, and then you can just treat the signs as they are. So I want opposite coefficients. Sometimes you'll hear me say the phrase inverse operation. Not inverse operation, additive inverses. You'll sometimes hear me say the phrase additive inverses. We're going to add, not subtract, if we're going to use inverse coefficients, additive inverses. Add the equations to eliminate one of the variables and solve the resulting equation. So in this set right here, we'll get back to this, you can add down these lists, and what you'll get is an elimination of a variable. 3x plus 3x is 6x, 2y plus negative 2y, or 2y minus 2y, is 0. Those ones eliminated in that state. 4 minus 4, those eliminate as well, but they become 0. The whole goal is to get rid of a variable set and solve for the current variable that you have. So 4 minus 4 is 0, 6x equals 0 is now your equation, and you can use that to solve for x. You divide both sides by 6. 6 times what is 0? 0. So x equals 0. And then from there, look, the elimination method, generally, we use the elimination part for just the first variable. After that, we kind of technically use substitution. So what are they going to do next? Substitute. Substitute the value from step 3 into one of the original equations and solve for the other variable. So we solve for x, we got 0. Now we can substitute it into an equation that contained x and contained y, because now we have to solve for y from there. So we had two equations to begin with. I know I crossed it out, and I'm going to have a habit of doing that. But 3x plus 2y equals 4, 3x minus 2y equals negative 4. I probably prefer this one, so does the book. It has all positives. You don't have to divide by a negative at that stage. So they're taking this equation, and they're substituting their x value, 0, and they're solving for y. 3 times 0 is 0, 2y equals 4, divide both sides by 2, you get y equals 2. And if x equals 0 and y equals 2, then your ordered pair is 0, 2. And of course, that's your final answer we're going to be writing here. So the elimination method can be used just like substitution method to get a variable by itself and then solve for it, but we'll use substitution afterward to do the rest. Could have I used elimination to then get rid of the x's or something? Sure. And I'm probably leading this portion before they talk about it. But you notice how they said you could multiply one or both equations by a constant, so terms have opposite coefficients. If I wanted to eliminate x's here, maybe I could multiply the bottom equation by -1. So this would become a -3x, a positive 2y, and a positive 4. And then in that case, now the x's would eliminate. You get gone and get 4y equals, and 4 plus 4 is 8. And divide both sides by 4, you get y equals 2. So we've seen that, right? We got y equals 2 before. Am I going to use elimination twice? No, probably not. I'm going to use elimination the first time and do substitution here. Now, I think you'll enjoy this method. I do want to still give the benefit to substitution method when it feels good to use. And I'll tell you what, I would not want to use substitution here because no matter what variable I get by itself, I'll always at least have one fraction. But in the substitution method, when you get a variable by itself and I do the substitution after, it feels a lot nicer to just have it say y equals whatever and then plugging in the x inside there. So that's one of the good benefits of substitution I enjoy. Elimination is pretty good, especially when you're already in standard form or a set of variables have already additive inverse coefficients, which is good. They did some double checking. I'm not going to double check unless I kind of am required to. All right, let's do another one. And this time we're going to have to do some form of multiplication here. Now, this is another strategic based element where they say, which variable would you like to eliminate? You know, what are you going to do with that? They state multiply equation 2 by -2 so that the coefficients of the x terms are opposites. Now, this actually isn't what I would have done. There's nothing wrong with it, but strategically, I try and multiply by as few negatives as possible. That being said, they took the bottom equation and they multiplied both sides by -2. Remember, you can do anything to one side of the equation as long as you do to the other side of the equation. And I'm going to lead into why we're even allowed to do elimination in the first place with that in mind. But if we multiply the bottom equation by -2, distribute that, these turn positive and they get doubled. You get 10x plus 12y from that right there. And -2 times 23 is -46. Don't forget to multiply the right side. That is a common missed element from students that I'm very well aware of, that they kind of tend to forget that. And remember, if you make one little mistake on these things, it leads to, well, not only the wrong answer, but you lead down a fraction hole. And then you're like, oh, this is kind of unnerving, and I get it. So anyway, they multiplied by -2 here to do this. Now, why did they do that? Because they're trying to align. If you added down these lists right now, no variables would eliminate. -10x minus 5x is -15x. 3y minus 6y is -3y. Nothing eliminated. But now when you multiply this bottom equation by -2, I have a -10x and a positive 10x. And now when you add down these lists, they eliminate. -10x plus 10x is 0x or 0. So they're gone. You add down here, boom, boom, and boom, boom, and you can solve for y. Then we'll take that -y, substitute it into an equation. They decided to use the bottom equation here. I don't know if I would have used it. It's okay, whatever. And then they solve for x. They get x equals -1, and that's your solution set. Now, let me talk about two more things from this example before we move forward. First of all, well, actually, let me see what they're saying here. Okay, I'm good. Okay, first of all, what I probably would have done just as a personal preference is I probably would have instead multiplied the top equation by 2. Now, the reason why is because I already see that these signs are opposite of each other, and I'm not multiplying by anything any larger than I would have by doing this bottom equation by -2, right? It's still times 2. So when it comes to picking preference, I like to try and avoid sign switching if possible. And that's not so much for me, it's more so for students who I'm teaching it to. Less mistakes would be made here. So if I multiply the top equation by 2 instead, this would now say -20x plus 6y equals 2. Now, when push comes to shove, you might say, well, Mr. Robinson, now you have negatives on your x's. True. I'm just stating when it comes to distributing negatives, some more things can go wrong here. I feel like forgetting to turn things positive, if not from the first time, then the second time. I feel like more things can go wrong. But notice the -6y and positive 6y will eliminate. So again, when push comes to shove, if I can find something that I'm multiplying by the same absolute value of at least, and I'm not doing too much to try and get something by itself, I want to see ones that have different signs, and that's going to be a me thing. Also, and this isn't the case for this kind of question here, sometimes I look to divide numbers. If I could have divided this set by 2, for example, like made this a -3y, that would have been good. Problem is, these are odd numbers, so I don't want to divide them by 2. So I guarantee you, you will see me divide if there's something where all numbers are divisible by the same value, and I can shrink to a number rather than grow to a number. I'm going to try that. Now let's talk about elimination and the method and why it works. And keep in mind, we could have done subtraction of them, right? They encouraged it. They said, hey, do subtraction at times when they have the same. Again, I'm not going to do that, but you can do that. You're allowed to mathematically do that. I just won't. Now, why can we add down these lists like this and make this happen? Well, number one, keep in mind, we want to align them so that we know what sides of the equation things are on and what terms combine. And we are using the benefit of combining like terms. We're using combining like terms to its benefit. So remember, this side equals this side. These sides are equivalent. For all intents and purposes, we could have rewritten this thing here as negative 46, and there's nothing wrong with it because it equals negative 46, right? But it doesn't help us because negative 10x plus negative 46 don't combine. They don't eliminate. So we like putting on this side what this is. These equal each other. Remember when I said multiply both sides by 2 or by negative 2? You could do anything to one side of the equation as long as you do it to the other. Well, I'm adding this to the left side of the equation, and I'm adding this to the right side of the equation. I'm allowed to do one thing to one side as long as I do the same thing to the other side. And are these the same thing? Yeah, they are equivalent expressions. It's like I'm adding negative 46 to both sides, but in this case, I'm adding an expression here that contains variables in it. So this is why this is allowed and what we're doing with it, but you want to use it to your advantage. Get additive inverses. Trust me, you're going to want it. Just treat the signs as they are from there and make sure everything's lined up so that they're on the proper sides of the equation, like terms are combined, things like that. Okay, we're looking at different methods. We've talked about solving by graphing. It's to estimate solutions, sure. I prefer using graphing when I have especially something like slope-intercept form for both equations, and especially when those slopes are fractions. That's probably a really good time to use the graphing set, but they also need to be within window range, have an integer set of solutions. So it's a good estimation. It's a good idea of understanding why we write ordered pairs, things like that. Not my favorite, but it has its benefits. Substitution. When you have, well, this is how they say it. One of the variables has a coefficient of 1 or negative 1, and I'm good with it. They're saying it's an easy way to get your variable by itself with no fraction hassle, and I get it. I'm good with that. When a variable's by itself as well. When it says y equals or x equals like that, it's good. Otherwise, elimination, you got some standard form set. You have opposite coefficients. Same coefficients is good. You just got to multiply an equation by negative 1. But when you're in standard form, x's and y's are lined up. Hey, they're really close to just eliminating. You just got to turn this sign negative and all the other ones. That'll be good. Or they're set up already. That'll be good. And I'm going to say that often. I'm going to say, if I added right now, would a variable eliminate? Not subtracted, but if I added right now, would a variable eliminate? If the answer is yes, do it. If the answer is no, what do we change? Which variable would you like to eliminate? What are you going to multiply or divide by? Things like that. And they talk about multiplying first. When one of them cannot be eliminated by adding or subtracting, I guess that gets back to my question, when we, and again, not adding or not subtracting. If I added right now, would a variable eliminate? Well, we'll have to multiply first in that scenario. Now, this is the elimination section, so I assume we're going to be focusing on elimination in a vacuum. But when we hit the review stuff, get ready to also use substitution. All right, let's do a word problem, and then we'll probably get to the problem set. A business with 2 locations buys 7 large delivery vans and 5 small delivery vans. Location A receives 5 large vans and 2 small vans for a total cost of $235,000. Location B, 2 large vans, 3 small vans for $160,000. What is the cost of each type of van? So this is large and small. We could use L and S. I'll probably use X and Y. They'll probably use X and Y. Yes, they do. So 5 vans times the cost of each large van, X, plus 2 small vans times the cost of each small van, Y, equals that, and 2x plus 3y equals that. Again, they define their variables as cost of large van is x, cost of small van is y. Not just let x equal large van, y equals small van. And I stated that before. That's not specific enough as far as what you're setting up. Doesn't help you with your equations that you set up. Doesn't help you with writing out your solution set. Be specific about what we're talking about. These are costs, not number of, not how many seats, not their weight, not their mileage, nothing like that. Anyway, set these things up and solve, and let's use elimination. This one gets a little, and I'm glad they're doing this one, because right now, obviously, if I added down these lists, nothing would eliminate. These aren't additive inverses, anything like that. But this one's interesting, because this one, there's no integer that I can multiply the bottom equation by, or the top equation by to get additive inverses for my variables. 5 is not a multiple of 2, and 3 is not a multiple of 2. So this time, I might have to multiply using both equations. So which one are they going to do? Looks like they're going to try and eliminate y's, and I'd probably do the same thing. You deal with smaller numbers that way. If I multiply the top equation by -3, right here, multiply everything by -3, it looks like our goal is to get the common multiple of 6. So if I multiply everything by here by -3, we get this, a -6y. Let's turn this into a positive 6y by multiplying by, well, 2. Multiply that by 2, distribute that, and we get this. Now we've created additive inverse coefficients, there's that word, coefficients, to eliminate our y's, and that's what's going to happen here when we add down the rest of the list. Treat the signs as they are. Boom, boom, -11x, boom, boom, maybe use the calculator, and divide, and you get an x of 35,000. That's the cost of the large van. Cost of each large van is 35,000. Or was that number of vans? I think it's cost. And then, again, you do a substitution for that. You could do an elimination thing. If I wanted to eliminate x's, I would multiply the bottom equation, say, by -5 and the top equation by +2. You'd get 10x and -10x. You could do that. But, of course, now that you have your x, you can substitute it into one of the equations and solve for y, and they did exactly that. Now, they had an ordered pair here of 35,000, 30,000, but it is a word problem. So each large van costs 35,000, each small van costs $30,000, right? Dollars. Okay. Okay, that looks to be the end of the lecture portion. Let's go into the vocabulary and core concept check before we do up to problem number 35 for this set. Give an example of a system of linear equations that can be solved by first adding the equations to eliminate one variable. So in this case here, I believe they're stating that it's already set up for you to do that. So let's say we had something like 3x plus 4y equals 12 and -3x plus, this probably won't give you a handsome answer. I'll just say plus y equals, let's say 3. I think that would work well. If I wanted to eliminate a variable, I could right now. I could do the addition of down these lists. They're all lined up and ready to go. If I added right now, the x's would go away. Adding a negative becomes subtraction. Gone, eliminated. 4y plus y is 5y. 12 plus 3 is 15, etc. Divide both sides here. You get y. I'm going to solve this one straight up. You get y equals 3. Now substitute 3 into an equation. I think if you do it right, you get x equals 0. But and then 0, 3 is your answer. But that eliminates the variable straight up because they already have additive inverse coefficients like that. And that's what we're looking to do. You probably shouldn't eliminate that. But actually, yeah, let's get rid of, I just wanted the answer to the setup. Thanks for the setup. So there's number 1. There's number 1, okay? Number 2, explain how to solve the system of linear equations by elimination. Okay, so from here, this is where we can talk shop and strategy. We ask ourselves right now, if we added down these lists, would any variable, not coefficients, or not constants, but would any variable eliminate? No. You get -3x plus 6y equals 3. Now, you pick and choose. Which variable would you like to eliminate by multiplying an equation by something, x or y? Well, we saw in the last example that 2 and 5, their common multiple is not 5. It's 10. You'd have to multiply both equations by something here. Whereas the y's, you only need to multiply the top equation by something to eliminate the y's, because 9 is a common multiple of 3. And because the 3 is negative, it's also nice that I can just multiply by a positive 3 and be good. So first thing I'm going to do is multiply the top equation there by 3 to turn that into a -9y. And I don't know if I need to do the full explanation after that y's eliminate. I solve for x, etc. So I'm not really going to show more steps. But multiply the top equation by 3. That means both sides by 3 to eliminate y's and solve for x. Once x is solved for, substitute into an original equation and solve for y. Right final answer is an ordered pair, right? That would be our last thing that we do there. So that's my description for that. That's my strategy involved. Could I eliminate x's? Yes. Would it take more steps? Yes. And I'm going to solve for x using kind of a substitution thereafter. Okay, guys, it looks like we're going to start with some eliminate. Well, of course, it's the section, but it looks like they're already primed and set up for elimination. It looks like they're all in standard form. Actually, some require some turnaround and work, which is good. We'll go ahead and get started here together. Numbers 3 through 10, we are going to solve the system by elimination. They do say check your solution. Of course, that'll probably be a mental math thing for me. So let's start with number 3. We have x plus 2y equals 13 and -x plus y equals 5. Now, if you were hearing me from the jump, what we have already is Sorry, I want to kind of move these over. I like to curly brace systems for some reason. I felt like it was missing without it, so like that. Maybe, maybe not. Maybe that gets in the way. But they're setting you up already to eliminate variables. They want to start that from the jump. X's can eliminate if I add down the list because x plus negative x is 0. So when these eliminate like that, you have 2y plus y is 3y, and 13 plus 5 is 18. Divide both sides by 3, you get y equals 6. And I didn't mention this from the jump, guys, but as a reminder, if you haven't heard my videos from section 5.1 and 5.2, from here on out, I am not showing the actions in between. This is probably the last time I'm going to say this, except for maybe a review. But I'm not going to show the actions in between steps of problems. I'm not going to write divided by 3 like that anymore, cross them out. So kind of get used to that notion we're there. Now, we're not done. We solve for y, great, but we also need to solve for x. Choose an equation to solve for x with. How about the top one? We have x plus 2 times 6, now that we know that y is 6, equals 13. And x plus 12 equals 13. Subtract 12 from both sides, you get x equals 1. Your solution ordered pair is 1, 6. Now, let's not lose sight of what it means to solve a system. What we did was we found the x and y, the one xy solution that works for both equations simultaneously. 1, 6 works for both the top equation and bottom equation. Of course, they asked us to double check. So 1 plus 12 equals 13. Negative 1 plus 6 equals 5. Those are true. Number 4. All right, 9x. I probably won't do the curly brace thing unless I feel it's better off. I don't think for these problems, since I got to multiply by stuff sometimes, that I'm going to use the curly brace set. All right, right now, if I added down these lists, right, first of all, is everything lined up? Yes. If I added down these, would a variable eliminate? Yes, the y's would eliminate. So when I go right here, y's go away. They're additive inverses. 9x minus 4x is 5x. 2 minus 17 is negative 15. And keep in mind, I am adding down these lists, just adding negatives become subtraction. That is still addition. Just like when we did subtraction for like slope formulas and stuff like that. Oh, sure, 6 minus negative 2 becomes 6 plus 2. Doesn't mean we didn't subtract those two numbers. And we divide both sides by 5, you get x equals negative 3. When we solve for y, we do a substitution into an equation. I like the top one because it shows a y, just a positive y. So 9 times negative 3 plus y, or negative 27 plus y, equals 2. Add 27 to both sides, you get y equals 29. A little bit bigger. And we get an ordered pair there of negative 3, 29. As a double check, we kind of just did the top equation, but try it again. Negative 27 plus 29 is 2. Negative 4 times negative 3 is 12. 12 minus 27 is negative 17. Okay. Number 5. Still more on the additive inverse front. It doesn't look like it had gone away yet. In fact, well, the first 6 problems don't seem to shy away from it. So you really get a good lead in on elimination and you say, this is awesome. I want to use this every day. Well, sometimes you have to do some equation manipulation and we'll get into those. But yeah, for the time being, guys, I would not solve these using substitution. As easy as it is to get this x by itself by adding 6y to both sides, it's easier right now to add down these lists. These 6y's eliminate, right? They're gone. You have 6x equals, and this is 24. Divide both sides by 6 and you get x equals 4. What's nice about these ones too with elimination is there's only one more step to solve. It's just division. It's like when you find your x and y intercepts, right? When one of the variables goes away, it's just a division left to go. Now the substitution takes a little bit more time, not much. Let's do, say, the bottom equation. We have, the top equation. We're solving for y, not x. 5 times 4 plus 6y equals 50. And 20 plus 6y equals 50. And 6y equals 30. Subtract 20. Divide by 6. You get y equals 5. So we have 4 comma 5. Is that solution set? Since I just did that on the top equation, let's try the bottom equation, see if that works. 4 minus 30 is negative 26. Everything went better than expected. Number 6. Which variables would eliminate if we added right now? Yep, the x's. Okay. Adding down these lists right now, x is begown. And y plus 3y is 4y. 4 plus 4 is 8. Divide both sides by 4, you get y equals 2. Let's do the top equation this time. I know it has a negative x there, but let's deal. Negative x plus 2 is 4. If I subtract 2, negative x is positive 2. Therefore, x is negative 2, right? multiply, divide both sides by -1, switch the signs around, whatever you want to state there, you get -2 comma 2, like so. Let's double check the bottom equation with that. -2 plus 6 is indeed 4. And we're good. Okay, here on out, I probably won't draw the cross-out thing. Just note that once you have additive inverses, those are the ones that we will eliminate, just so it's not too messy. So -3, especially because here's the thing. We have to go back to our equations, right? One of them to do substitution, and you're like, I can't see behind the thing that's crossed out. I might, by habit, cross them out sometimes, but right now I'm very consciously aware, very cognizant of the fact that I'm not going to. So I'm going to eliminate the y's because they're additive inverses. Now let's add down the lists. -7x equals 14 minus 7 is 7. Divide by -7, you get x equals -1. I kind of feel like I want to cross them out, but I just don't want to get it in the way of what we have next. Let's solve for y. Let's substitute in the bottom equation, say, and we'll have -4 times -1 there, and that's 4. Subtract 4 from both sides and divide both sides by 5. You get a y value of 2. So -1, 2 is our ordered pair. Again, point of intersection where these two lines would cross with each other. Check the top equation. -3 times -1 is 3. -5 times 2 is -10. And 3 minus 10 is -7. Number 8. (4x minus 9y equals -4x). Okay. Y's do not eliminate. I was going to say they do. X's eliminate. Boom. -9y minus 3y is here. -21 plus 9 is here. Divide by -12, you get y equals 1. So far, they haven't had any sort of fraction versions of answers. If we get some like 1/2 or something, it's no big. That's fine. But in getting integer answers, you almost trust you're doing the work right. If you got a random fraction answer like 5/13, sometimes you'll question it. I know when I did my IM3 videos for this kind of stuff, that happened more often than I liked. So that was something that I was like, I don't know if I got these answers right. I'm going to trust my own version of my math. And sure enough, I believe those were correct because I definitely didn't do double checks. And yes, I want to mention this right now. You might not see, as much as I was hating on arithmetic sequences, saying you won't see this again until IM3, you might not see systems of equations very much in IM2 at all. You might not see those until IM3 for quite a while. I think, though, that these run the gamut of doing things. Listen, we do substitution and graphing and things like that. Elimination, not so much in more commonplace elements, but we use them all around our algebra stuff that we have anyway. So they're very good tactics to utilize. So even if we don't talk about systems very often in IM2 or moving forward after this set, and you don't see them again until IM3 and not for very long, I'm good with having them here. You're still practicing good algebra tactics. Arithmetic sequences kind of fly in the way of other things sometimes, and that's why I was kind of poo-pooing on them. Anyway, -3 in the bottom equation gives you 12. -3 right there gives you 9, and that one looks to work. Okay, numbers 9 and 10 are slightly altered. Let's talk about them. The alteration here is that the equations aren't lined up, and that's kind of what I noticed immediately when I was saying that they're all in standard form. This isn't really in standard form right now. Now, they are asking us to use the elimination method, so even if I could get a y variable by itself plenty easily, we're not going to use substitution. My recommendation is actually get it in standard form. Get the appearance of, well, this bottom equation. An x, then a y, then a constant. It's something we're very familiar with, and we like familiar. That means I need to take, say, this top equation, and if I subtract 6x from both sides, then it would be over here with the -y. And if I add 10 to both sides, boom, on this side, then we actually, get standard form. And this one, just not rewritten, but not rearranged, is 5x plus y equals -10. And we are actually in a state now in standard form that things are lined up, but also y's can eliminate. So we're actually there right now. So if we add down the list, we get -6x plus 5x is -1x. And 10 minus 10, don't say eliminate, it becomes 0. If -x is 0, then positive x also equals 0, right? There's the answer. We haven't gotten a lot of, and I've stated this back since chapter 1, there haven't been a lot of times that we've gotten, x equals 0, y equals 0 kinds of answers. And we want to still be comfortable with them. It doesn't mean no solution, right? 0 is literally the number that we substitute. Case in point, let's do that here with one of our equations like this bottom one. 5 times 0, of course, is 0. And that means that goes away. So our y value is negative 10. So we get 0, negative 10 is our solution set. If we double check it with the top, negative y, opposite of negative 10 is 10. 10 minus 10 is 6 times 0, which is 0. 10 minus 10 is 0. That is good. Okay, number 10. Once again, things aren't lined up as they should be. Don't just start adding down lists just because. It actually would be to no effect if things can't combine. Now, they don't have the equations set up the way that I thought they would, where people might make mistakes in not rewriting equations, and it really has to do with having the equal sign not lined up with terms on opposite sides. I'll maybe show you what I mean later if they don't actually do it. Like I said, let's just do a standard form appearance thing. Let's say, keep the x on this side, 3x, subtract y over, and then add the 30 over to this side, like so. And then take this one, subtract 3x over, and that's good. You get additive inverses here. You have that positive 7y, and then add the 6 over to this side. Standard form, x's eliminate. Negative y plus 7y is 6y. 30 plus 6 is 36. Divide both sides by 6, you get y equals 6. You can take an original equation if you'd like to here. This y is already by itself. Well, let's do this bottom one. The 3x is by itself in a way. So 7 times 6 minus 6 equals 3x. That's 42 minus 6. Or 36. Notice how I wrote that on that side. Divide by 3, get x equals 12. So x equals 12, y equals 6. 12 comma 6 is our problem, solution to our problem set. Double check the top one. 36 minus 30 equals 6. Again, I'm doing 3 times 12, and I'm plugging in 6 for y. So that's all good. Okay, there's elimination where, I don't know, equations weren't really manipulated. The bottom ones were rearranged a little bit, but no multiplying or dividing both top and bottom by something. I'm sure that's going to happen in this next set. They say solve by elimination, check your solutions, but these are probably different kind of questions. They say see example 2. I think this is where we had to multiply by something. So on number 11, we have x plus y equals 2 and 2x plus 7y equals 9. Yes, so we have everything lined up, but if we added right now down these lists, we get this. Now, could this operate in our system, meaning the same x's and y's, that the same x and y that works for the solution to this system, would it work here as well? It would. It absolutely would. Is this eliminating a variable and helping us solve for those x's and y's? No. Adding down these lists did nothing for us right now, not unless a variable could eliminate. So what I'm going to do is equation manipulation. I'd like to eliminate, say, my x's by multiplying top and just both left and right here by negative 2. That turns this into a negative 2x. Therefore, these can eliminate. And I get negative 2y here. And here I get negative 4. Don't forget to add that side of the equation. Or multiply that side of the equation. Could have I eliminated y's by multiplying this top equation by negative 7? Sure. Do the numbers become bigger? Yeah. So I'm going to choose the x's. So in eliminating that, those go away. 7y minus 2y is 5y. 9 minus 4 is 5. And divide by 5, you get y equals 1. So more of the same as before. I'd like to use this original top equation, x plus y equals 2. Subtract 1 to get x equals 1. So 1, 1 is our ordered pair solution set. And to remind you, the thing that I added before, let's see, x plus 2x was 3x, y plus 7y was 8y, equals 2 plus 11, or 2 plus 9 is 11. 3 times 1 plus 8 times 1 does indeed equal 11. So it would have worked for that set that we added down for. It's just that that didn't help us solve. So there was no need. So that's number 11. Let's go to number 12. On number 12, once again, if I added down either list, 8x plus 4x, don't eliminate. Negative 5y plus 3y, don't eliminate. Or plus negative 3y, don't eliminate. So let's eliminate a variable. Be strategic, make a conscious choice. If I tried to eliminate y's, I'd have to manipulate both equations because I need a least common multiple, and that would be a 15. Whereas here, the least common multiple of 4 and 8 is actually just 8. So I can take this bottom equation, multiply everything by negative 2. It's kind of like that top one we had. And then I can rewrite that into negative 8x plus 6y equals negative 10. Your organization on this stuff is up to you and how you want to work this out. Really what I want to look at is the top equation and this newly written bottom equation. So if I want to hide this one temporarily, I can. Of course, mind you, I can hit the undo button or do something like this with it. Maybe you can't on your piece of paper. But I'm adding down these lists right here, and I just want to show you them for what they are. So if I add down the lists right now, x's would eliminate. Be gone. Negative 5y plus 6y is 1y. Perfect. And 11 minus 10 is 1. Perfect. So when I solve for x, I can use any of these equations, this, or that, to solve for x. Maybe just use this one down here. Why not? The 6y. Oh, actually, because we're not solving for y, we're solving for x. So let's use this equation. I would have loved to use this equation for it, to be honest, but I can't see it. So 8x minus 5 times 1 equals 11. And 5 times 1 is 5. Add 5 to both sides and divide by 8 to get x equals 2. So we get 2, 1. That's checking the, that was with the top equation. Let's check that bottom original equation, make sure that that does work out. That's 8 minus 3, and that is 5. So that's all good. Now let's cross it out all over again in case you did the same thing. So again, your organization is up to you. Do you want to use different colors like I am? Do you want to just rewrite both equations right next to each other? Is it okay overlaying one? It's kind of up to you on how you want to make that happen. Number 13. Okay. 11x minus 20. Number's getting a little bigger. It's okay. Okay. Adding down the lists right now would do nothing as far as elimination goes. So, which variable would you like to eliminate? Why? Because I'm asking you. I'm asking you, which variable would you like to eliminate? Because it helps us solve the equation. That's why. Oh, you mean why the variable? Oh, that's what you were saying. Okay. I'm sorry about that. Sorry, this isn't quite Dora the Explorer or Blue's Clues, but I like to do that in my class a lot. They're like, why? Why? Because I want to know. Stop being so inquisitive. Jeez. Okay. Yeah. Let's eliminate y. There are two benefits to eliminating y for me here. Number one, I only need to multiply one equation by something, in which case the bottom equation, multiply by 5. Number two, I don't need to change any signs. This one's negative, this one's positive. Really, number one matters more, but if push came to shove and I had to choose, I'd rather choose the one where I probably don't have to change signs. Let's multiply the bottom equation here by 5. And again, if you want to do a rewrite of both equations just so they're next to each other, go ahead and do that. So 11x minus 20y equals 28, and here 15x plus 20y equals, and 36 times 5 is 180. Geez, those are big numbers. Well, I'm still the best method. Even if substitution was an option opted for me, I'm going to use elimination. This is exactly what I'm going to do. No worries there. These eliminate. I have 26x equals 208. I guess those divide evenly. X equals, must be 8 because I'm just going to have to assume that it's 8. We'll double check that later. Oh, yeah, that's 8. That's good. Okay. Solve for y now, and I'd love to use that original equation. This is good that I didn't cross it out. I'd love to use this one. It's the smallest set of what I have. Y is positive. So let's do 3 times x plus 4y equals 36. 24 plus 4y equals 36. And subtract 24, get 12. Divide, you get y equals 3. Makes me more confident that that x was actually 8. So I get 8 comma 3. Let's double check with the top, just in case something went wrong. 88 minus 60, that's 28. Okay. You know, I'm looking at all the other problems here just to kind of see if there's something I wanted to do with them. And this textbook is not offering me something I want to do, which is, and it's fine, but I've mentioned that I might do division of values to get an additive inverse of a variable. It's not the case here. Every problem is broken down so that there is no greatest common factor to any of these equations other than 1. And I'm looking at all the equations here downward. There's no time I can divide everything by 2 or 3 or 7 or something like that to just get them smaller. So that whole division thing that I was talking about, it's not going to apply, at least with these problems here. We'll see if it does later, but not yet. We'll see if they do later. I know there are other, if you want to find other videos of mine, we can do that. Okay, nothing eliminates just yet, so we have to make a choice. Would you rather eliminate x or y? And honestly, either's pretty good. I can multiply the bottom equation by 5 and eliminate x's, or the bottom equation by 3 and eliminate y's. I guess multiply by the smaller number, so 3. But either is good because signs are already opposite of each other. Those numbers are not very small, and you only have to do it just once, right? You don't have to multiply both equations. So 10x minus 9y equals 46 is the top equation. And here I have negative 6x plus 9y equals, is it 10? No, it's 30. And now the y's eliminate here. Maybe we can do this for this problem, though, just because it's so already set up for us to do it this way. Divide by 4 and get x equals 19. But check this out. Let's do elimination. Let's now solve for y. I'm going to make this blue just so we know that this was eliminating x. Let's now solve for y using elimination as well, right? Normally we do a substitution, right? Plug 19 into here, solve for y. Let's do this now instead, though. I'm going to make this green just to show you. Let's now multiply that bottom equation by 5, and let's look at it this way to eliminate x's. Now it's negative 10x plus 15y equals 50. And now when we add down the list, x's eliminate, you get 6y equals 96, and divide both sides by 6, you get 9. Is that 16? Y is 16. Y equals 16. So you get 19 for x, 16 for y. We can double check it. The numbers will be kind of big. I think it's almost worth just moving forward. But that'll be 190 minus 16 is 144, right? 180 minus 144. Wait. Is that right? 180 minus 144? Well, 190. 190 minus 144, that is 46, yes. And then negative 2, that's negative 38 plus 48. That should be 10, equals 10. Yes, those work out. So this is the first instance where I actually, and it was just to show you that both were fair game. They were actually pretty decent. But also that was using pure elimination. I mean, the elimination method allows you to use substitution afterward. Like when they say use the method, we do substitution afterward all the time, right? Just like this one right here. Pure elimination was eliminate the x's to solve for y's, eliminate the y's to solve for x's, whatever like that. And no substitution was ever done. So do you like that more? I don't. I just do. I prefer doing a substitution after I solve for one of them personally. But that was pretty fair game to do it. Both of them seemed pretty feasible, and I wanted to show you the feasibility of both of them. All right, number 15. This is where things get a little, you got to do a little more. When you look at these numbers here, you see that neither coefficient is a common multiple of the other smaller version of a number. And yeah, you got to start making choices. Nothing will eliminate right now, so let's do some equation manipulation to make it so. Would you rather eliminate x's or y's? And this one is kind of a pick and choose. If you wanted smaller numbers overall, you want to eliminate y's because 3 and 2 have a smaller least common multiple of 6, then 4 and 5 having a least common multiple of 20. To eliminate x's, I'd have to multiply the top equation by 5 and the bottom equation by 4. Of course, I'd make one of them negative, but I'd have to do times 5 times 4. On these ones, I can multiply the top equation by 2, the bottom equation by 3, and the variables would then eliminate there. So let's do the y's. Let's do top equation times, let's make this one positive 2, and let's make the bottom one negative 3. And again, I'd love to keep them as additive inverses, so I need to change one of the signs here. So we'll get 8x minus 6y equals 16 on top. And on bottom, we'll get negative 15x plus 6y, that's why I wanted the negative there, equals positive 33. 8 minus 15 is negative 7. Y's eliminate, and you get 49 there. As you know, that divides evenly. You get x is negative 7. And now we can do a substitution. Let's do, both the y's are negative here anyway. Let's just do the bottom equation. Okay, negative 35. And if I add 35 to both sides, I'm doing 35 minus 11, which is 24. Divide by negative 2, you get y is negative 12. So negative 7 for x, negative 12 for y. Are you liking this method so far? I think most people do. They're like, yeah, I get this. I like this. Well, substitution, forget that. Remember, it depends on the situation. But in these situations, getting these x's or y's by themselves would lead to fractions. So I'm using elimination for a problem like this regardless. Trust me. It's all problem dependent, guys. I know we're living in a vacuum with this set of elimination. Again, most people like it, but don't force elimination if substitution is probably preferred. Anyway, negative 7, negative 12. Check this top one. Negative 28 plus 36 is 8. So we got 8 there, yes. All right, I'm going to imagine that all the rest of them moving forward need to manipulate both equations. So kind of get ready for those. And it just, besides word problems and, how do you see it and making an argument and error analysis, things like that. We'll see what other kinds of questions they have in store up to problem 35 because we're not even halfway through. By the time we get to number 18, we'll be halfway through. So what other questions do they have? I don't know. All right, let me take a sip while we... Okay, variables don't eliminate. Let's eliminate x or y, though. 5 and 11 have a common multiple of 55. 55. Kind of bigger than 6, so I'd like to eliminate the x's instead here. Let's multiply the top equation, and they're opposite signs already, but they are for y's as well. By 3 on top, by 2 on bottom, let's get rid of dem x's, and we get negative 6x minus 15y equals 27, and 6x plus 22y equals 8. X's eliminate, you get 7y equals 35. Divide by 7, you get y equals 5. Let's do the bottom equation. X's are everything's positive there. 33x plus 11 times 5. So 55 still shows up. Sometimes when I get a large answer like this, I'm like, I don't know. Oh, we're dividing by 3. Never mind. So negative 51 is still kind of big. That's negative 17. Sometimes I go, I don't know. We can double check, but if we're not graphing them, then hey, any answer can be what it is, especially when you hit word problems, right? You can get answers in thousands in word problems because it can represent money and things like that. So negative 17 comma 5, 34 minus 25 is 9. So that does work. Notice I have been double checking, just mentally. Okay. Now, if you check my YouTube channel, you do see my YouTube channel is not laid out perfectly, but type, Robinson Math, Mr. Robinson, something like that on the top. If you typed elimination after that, you'll see more. This is not my only video on elimination. You'll find other ones where I do talk about things with special cases. We haven't seen special cases yet, but special cases, you'll see me do those division option things. So if they don't show up here, if I'm like, hey, I can divide all these, by 3. If this was a 3y right here, I'm like, hey, divide all these by 3 and then something. Make them smaller first because we're only making numbers bigger. So just mind you, if you want to find more elimination type problems, you can see them through other videos that I have. I don't know where they are. Search them up. They're there somewhere. All right. Let's eliminate an x or a y here. I'm going to aim more for least common multiple things here. Least common multiple of 9 and 6 is 18. Least common multiple of 2 and 3 is 26. So if 18 leads to smaller number, smaller multiplication, let's do it. Both sets are positive, so it's not like there's a push comes to shove set there. So let's just do the x's. Eliminate those. I'll multiply the top equation by 2 and the bottom equation by negative 3. That'll get me a positive 18x and a negative 18x. Let's write negative 18 there. So here we'll get 18x plus 4y equals 78. And negative 18x minus 39y equals positive 27. Never said the numbers won't be big. Negative 35y equals positive 105. Those do divide. That's a y value of negative 3 when you divide by negative 35. Let's solve for x. Let's use the top equation here. 9x plus 2 times negative 3. Add 6, divide by 9. You get x equals 5. All right. Double check it with the bottom equation. That's 30 minus 39, and that's negative 9. Last one of this set, number 18. Again, nothing could divide. For shame. That's okay. But still for shame. Nothing to rearrange on these problems, though, right? It's just been working things out the way you'd like to. Okay. This is where you can make a conscious choice here. 12 and 8 have a least common multiple of 24. I can multiply one by 2, the other by 3, maybe one of them negative, and then we'll go. 7 and 11 have a least common multiple of 77. That makes numbers bigger. The signs are opposite. That's a nice part. But I'd say that's a little too big of a multiplication. Now I got to do 12 times 11, and then I got to add with 132. That's going to be a little big. Let's just stick with the x's on elimination here. Let's multiply the top, say by the negative this time. Let's do times negative 2. It turns these ones positive. and then the bottom by the positive 3. And here we'll get, I'll write it down below, I kind of ran out of room, negative 24x plus 14y equals 4. A lot of elimination of x recently. That's just nature of the beast, is you don't have to trade off each time. It doesn't really matter. 33y equals 90. X's will eliminate as we get 47, obscure number, 47x equals 94, but hey, 47 is half of 94. Divided by 47, you do get x equals 2, so that's nice. Let's do the bottom equation here. We got 8x, 8 times 2, plus 11y equals 30. Is that right? Is this going to be a fraction? Hold on a second. Did I do something wrong there? X equals 2. Did I do something wrong? 24x plus 33y equals 90. Add down the lists there. You get 47x equals 2. Because this is going to be a fraction. What did I do wrong? Negative 2, 8x plus 11y equals 30. Let me double check and make sure I didn't screw something up, because I don't want a fraction answer if it's not supposed to show up. Hold on. Why? Oh my goodness. That happened. All right. Y equals 2. Let's do that all over again. Now we solve for x. As far as error analysis goes, that's the only time I've ever made a silly mistake like that. And if that shows up on a thing where, hey, the y's turned into x's, I can't say that that doesn't happen, because suddenly it just did. All right, but at least I caught myself. And really it was getting a fraction, going like, I don't know, we haven't seen a fraction yet. Okay, let's solve for x's. Let's still do that bottom equation. We have 8x plus 11 times y equals 30. Aha, that looks better. 8x equals 8. When you subtract 22, divide both sides by 8, you get x equals 1. So 1 comma 2. And of course, as always, maybe it does sound good to double check these days. That's 12 minus 14, and that's negative 2, so that's good. Okay, fixed, all taken care of, we're set. At this point, you probably aren't watching this part of the solution guide video because you probably understand this by now. And you're like, I did this on my own. I made less mistakes than you did, Mr. Robinson. Speaking of, we have error analysis coming forward. Let's see if they make the silly mistake that I did. Describe and correct the error in solving for one of the variables in the linear system. 5x minus 7y equals 16. X plus 7y equals 8. Okay, they copied the problem down right. Their y's eliminated and okay, looks like they subtracted the x's here instead of adding, whereas here they added. This should say 5x plus x is 6x. Given that these are additive inverses, they did true addition. So this should be a 6x instead. And by the way, they're not done. It says solving for one of the variables. We're not solving the entire system. But they subtracted their x's, whereas they added all the other sets. See, if you do subtraction, that's fine. You just got to do it for everything. And in this case, subtraction wouldn't eliminate those y's, but this is addition, clearly from the other two sets of the y's and the constants that they had here. So the x's subtracted instead of added. They subtracted. So they have to do an addition of that. It doesn't look like we're solving the entire system though, so let's just do that one part. 5x minus 7y equals 16, and x plus 7y equals 8. When you add down those lists, y's do eliminate, right? But this becomes 6x, not 4x, equals 24, and that still divides evenly. You get x equals 4. They're not asking for the rest, so I'll leave it. That's it. Number 20, describe and correct the error here. We have the equation 4x plus 3y equals 8, x minus 2y equals negative 13. They decided to multiply by negative 4. I agree. I would do that as well. It just takes one equation to manipulate to do that. That's a negative. See, this is a common thing that people do, so I'm glad they caught it. Negative 13 never got multiplied by negative 4 here. That's what I first thought I made the mistake on problem 18 when I made my mistake. They didn't multiply it by negative 4. They have to do that, and that carries forward. Trust me, that's forgotten. Maybe not all the time, but that's the one part that's like, you're so focused on getting those variables eliminated that you lose sight of the fact that both parts need to multiply by that number. So I'm guessing that's their only mistake. Look, they got a fraction answer. Not to say that fraction answers can't be had, but it starts to make you question whether it's right or wrong. Not that it's no solution. Anyway, so when multiplying by negative 4, which I preferred, and I agree with, the negative 13 on the right side of the equation never multiplied. And I want to state once again, this is a common mistake. This is a common mishap on these things, including sign issues. Both of what they said for error analyses were actually quite common. Normally, people wouldn't subtract here unless they were... See, normally, people actually, if this was a plus 7, they would subtract these and then add these over. So they'd actually do opposite of what you see here, but that idea is still in place. This is actually a common thing that would happen. So let's take this again. 4x plus... And we're not solving the whole system, but just solving for one of the variables. So we have x minus 2y equals negative 13, and I would indeed as well multiply the bottom equation by negative 4. So now we'll have negative 4x plus 8y, which they had as well, but not negative 13, but negative 13 times 4, which is positive 52, I believe. Yeah. So 11y equals, well, it's still a fraction. 11y equals 60, and you divide by 11, you get y equals 60 over 11. So all the more reason to not solve the entire system. You still apparently get a fraction. Oh, well. And that's it. So no matter what, it seemed like it was a fraction problem. Number 21. So now we hit some word problems, right? We still have 15 problems to go, though. So number 21. A service center charges a fee of X dollars for an oil change, plus Y dollars per quart of oil used. A sample of its sales record is shown. Write a system of linear equations that represents the situation. Find the fee and cost per quart of oil. Charges a fee of X dollars for an oil change. So they're going to outright do that. So they have customer A was charged this amount. I'm going to kind of like write A and B to begin with here for my system to kind of make sense of it. So customer A is charged X dollars for a quart of oil. And then, see, should I define these? I think this one's going to be a little more straight up because actually they said it. X dollars and Y dollars per quart of oil. So they defined it for us. Y dollars per quart of oil used. It says find the fee and cost per quart of oil, which we don't know. But they have the sample of the sales and they say customer A, oil change, quart of oil. Here's the thing. I buy my own quarts of oil, so I only pay for the oil change portion. So I don't buy them at the place. So I don't know how this works. 5 quarts of oils required for customer A. So 5 quarts of oil times the cost per quart of oil in dollars. And that'll equal a total of $22.45. Customer B, on the other hand, has oil change and then $7 per quart of oil. And that's $25.45. Let's find those costs. Not by guess and check, but let's use elimination. And the x's are primed for elimination here, quite so. If I took, say, the top equation and multiplied by negative 1, and there's a reason I'm doing the top equation, not the bottom. Actually, 2 things help. Number 1, I don't have to rewrite the bottom equation if I put this right down below. Number 2, it keeps terms positive. That's something I kind of look ahead on sometimes if I'm able to. And the x's will eliminate here. We'll go ahead and cross them out. And now you have 2y equals... And listen, I'll deal with decimals to the extent that we no longer have to. 25.45 minus 22.45 is $3. So like that. And y is 1.5. Now there's more I'm going to state on that in a moment. This is the exact decimal answer your calculator would say. But when it comes to actual units, we might represent it a little bit differently. As you know, it's money. Let's now solve for x by using either set. Customer A will work out for me. X plus 5 times 1.5 equals 22.45. This basically shows... I'm paying how many dollars per oil change? Well, I'm paying $7.50, 7.5 here, for a quart of oil. Excuse me, for 5 quarts of oil. And somehow it turned to $77.45. That's the upcharge that oil change is due to you, folks. Make sure you double check on those things. Get a second opinion. Subtract 7.5. And at this point, I might as well say 750 because I got to subtract this over. 22.45 minus 750 is that $14.95? $14.95. So that's $14.95. And that's the point I want to make here, guys. We're not going to write an ordered pair this time. We can use word problem stuff, which means context, units, and the right form of decimals and stuff. The oil change will cost $14.95 flat, just up front. That's how much I'd be paying. And because I bought the quarts of oil elsewhere. And each quart of oil costs $1.50. And that's where I want to use that extra zero, right? When we say money, when it comes to cents, we use 2 decimal places. We don't say $1.5 or $1.50 even, or 3/2 of a dollar. So we will actually use the decimal version right there, and that's actually fine. Now, I'm not going to double check, but customer B should have been charged the same amount. As you see, they were charged $3 extra. So that makes sense where that extra $1.50 per quart comes into play for the 2 extra quarts that they have for the 1 oil change. Number 22. A music website charges X dollars for individual songs and Y dollars for entire albums. Person A pays $25.92. Oh, they're going to make me use the calculator at some point, won't they? To download 6 individual songs and 2 albums. Now, they already defined X and Y for us, so I can use that. So 6 individual songs times the cost per song, plus 2 individual albums times the cost per album, or 2 albums, equals $25.92. That's person A. Person B pays $33.93 total, in that they bought 4 individual songs and 3 albums. Write a system of linear equations. Done. How much does the website charge to download a song and entire album? So this is one where, listen, you can either, do this one or this one when it comes to elimination, right? X's or Y's. And I'm probably going to go for the Y's. But this is one where just because I can do it, I will. The top equation, I could divide everything by 2, including the dollar amount. And it's not going to affect, listen, I'll have decimals regardless, but it's not going to affect what it has. This is an even number because it ends in a 2. It's an even number, if you will. And I have to manipulate both equations anyway. I might as well take the top equation and divide by 2. Just to make numbers smaller first. It's not a requirement. No, by no means. No, it's not. But this becomes now 3x plus 1y equals, my only problem is I don't know what this is divided by 2. 1296? I think. Let's see. 12. Yeah, I think so. So 1296. Now, that didn't yet eliminate the variables, but it made things easy. It made things smaller. It's taking the same amount of steps as it would by multiplying both equations by something. But here's the thing. I'm still going to take this equation and manipulate it again. It looks like y's are ready to do elimination. But as you can do multiplication, but you can also do division. And I wanted to just show you that there. So if I multiply this equation now by -3, and I'm going to work it with this one here. We'll just get rewrites of both of them. I have 4x plus 3y equals 3393. And I have now -9x minus 3y equals, now I got to actually do the math here, but you would anyway. I don't want to mess up, so let's write it. 12. My calculator's kind of frozen here. 1296 times 3. I'm getting 3888, but negative 3888. Again, calculator may be used here in a second. But y's eliminate now, and you get -5x equals, let's not mess this up, 3393. 495. I think that's 99 cents. Oh, negative 495. I think that's 99 cents there. X equals 0.99. So 99 cents a song. Fair. I think iTunes does that. 99 cents a song for X. Y is a substitute. And look, I like this bottom equation more than anything else when it comes to solving for Y, right? Y is just Y. So 3 times 99 plus Y. Now, does this equation represent person A or B in particular? No. But this is still a situation that works for the system. That's the point. That's 297. Is this 999? That was my speculative answer prior to, but Y equals 999 there. So each individual song costs 99 cents. Each album costs $9.99. Again, it's a common iTunes thing. iTunes also does what? $129 or something. What else do they charge per song sometimes? What's their higher thing? I think it's $129, and their albums can be higher, $12.99. Each individual song costs 99 cents, and each album costs $9.99. Honestly, and you know me, I buy CDs still. I import, get my higher quality. I only do iTunes for things that aren't accessible for CD or something like that. or I want an individual song. Okay. Numbers 23 to 26. Solve the system of linear equations using any method. Okay, explain why you chose the method. So here's the thing. Although we're in the elimination section, I want to make arguments for and against, and I'm probably not going to solve by graphing. Well, actually take it back. Number 25, I might solve by graphing. I might solve by graphing on number 25, but I want to make arguments for or against why I might choose to use substitution for a problem. And, if I don't want to use substitution, then elimination is probably the way to go, right? So in a problem like this, would I use elimination, substitution, or graphing? Graphing is also still not bad for this one. But I'm going to go ahead and not use substitution because no matter which variable I get by itself, dividing by 3 or 2 or 2 or 5, it'll always create some fraction somewhere. And I don't want fractions unless it's a slope for graphing. Now, in graphing, it actually wouldn't be bad. Let's talk about that for a moment. I could subtract 3x from both sides. I was poo-pooing on graphing before, but just to show you as far as this goes, divide by 2, you get y equals negative 3 halves x plus 2. That's not bad, right? The y-intercept ain't a fraction. And for this one here, if I divide everything by 2, you get y equals, I'm going to put this one first, negative 5 halves x plus 4. Hey, guys, that's not a bad system for graphing. Maybe I'll graph and double check and make sure I still get the right answer. But there's a graphing version of this. I don't want to use substitution, though, for the very sake, like I stated, getting a variable by itself will lead to fractions. And I don't want fractions in my algebraic equations. But how will elimination work? And we'll do graphing afterward. How will elimination work? That's probably my preferred, really. But I got 3x plus 2y equals 4 here. And if I add 5x over, I get 5x plus 2y equals 8. See, my two y's are primed for elimination here. If you subtracted right now, they would, but of course, I'm more of a sign changing kind of dude. So multiply the top equation by -1, change all the signs, like that. And now we have something set up for elimination. Subtract, add down the list. 2x equals 4, therefore x equals 2. And in terms of solving for y, we can do let's do that top equation for substitution. 3 times 2 plus 2y equals 4, or 6 plus 2y equals 4, or I'm going to shift everything up, so I'm kind of running out of space here, or 2y equals -2 and y equals -1. So I got 2, -1 as my solution set. That was solving using elimination, probably the preferred, as we are in this section. I didn't doubt that they wanted to start with that. But let's look at the graphing version for a second. Slope-intercept form for both of them. Let me get some graph paper, copy it on up, and paste it on in. I got these two equations. They're in slope-intercept form. Fractions are fine for these things. Let's see if we cross at 2, -1. Let's remind ourselves what graphing looks like. And, of course, I'm probably going to do graphing for another problem here in a bit. Slope, y-intercept of 2, down 3, right 2, like this. Boom. 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 It's not common. You'd see me do the graphing thing here. Foist. I really looked to this one for last, but I just want to show you that it's there. Of course, like I said, I think number 25 I probably will solve by graphing. I'll probably use multiple methods. You know a video that I do have, and I forget what it's called, but it's one, and that's probably not very helpful for you, but there's one that I do, down 5 over 2, there's that 2, -1. There's one that I do that's like, it might be titled something like the pros and cons of solving systems using any method, whatever. I have a video, and I think I'll probably link it down below, but I have a video where I think I have 12 problems to do, and I choose which methods to solve, kind of like what we're doing right here. But I do any of them which are viable to do. So I would never use substitution for this one. I don't know if I'd do graphing, honestly. I'd probably just use elimination, but showing you graphing here. There are problems for which graphing is most preferred, but you can see here they cross once again at 2, -1. And there we have it. That's your solution set. So anyway, I'll link that video down below as well if you want to see me do some extra things with like when I use elimination, substitution, things like that for problems. And I think this is kind of more of the same with these kinds of questions. But you'll get more of them that way, which is nice. So this is kind of a review in a way that we're doing here. Number 24. See, substitution's calling for me on number 24. I have x by itself. Actually, I was thinking of getting y by itself on the bottom equation. I didn't realize x was already by itself. But I have x by itself already on this equation, right? I like substitution for this. You might go like, we could multiply these equations by 4. You could. The variable won't be by itself on its own side of the equation if I eliminated x right there. You could. And I probably will. But let's start with substitution. I'll do it in blue. Say I'll put an S for substitution. For substitution, x is by itself. Y minus 2 can take x's place, and you can, boom, plug it in right there. So I got negative 6y plus 2 equals negative 4 times this y minus 2. That's my x. And you can decide for yourself whether this looks better for you or not. I can add 6y to both sides to make it positive. Subtract 8 from both sides. I guess that makes that negative. Divide by 2, you get y equals negative 3. What's nice about this is x is already by itself. Here's the substitution thing. Here's what I like about it. X equals y minus 2. So negative 3 minus 2 is negative 5. Now our ordered pair will be negative 5 comma negative 3. So given that x was already isolated, or it would have just taken one step to isolate y even, I really like substitution there. See, this isn't yet in standard form. And although it's not in standard form, it still has variables on their own sides of the equation. So for elimination, yeah, I could have multiplied, say, the whole bottom equation by 4. And now I would have this original top equation. And the bottom equation would now say 4y minus 8 equals 4x. Did I get it in standard form? No, but are things lined up, including the equal sign? Yes. So will that still help? Sort of. The variables eliminate here and you get 0. And on this same side of the equation, you got a negative 6 and a negative 2y. So there's still more work to do. I have to add 6 over, whatever. Add 6 over and divide by negative 2. You get y equals negative 3. So you still get there, right? I feel like a little more work was needed on the elimination portion of that. I'm not done. I still have to solve for x, which I guess this x is still by itself. That's not wrong. So x is negative 3 minus 2, which is negative 5. And we still get the same answer. I'm not going to graph those ones. And I probably wouldn't want to. Getting a fraction y-intercept on that wouldn't be any fun. Number 25. Look, number 25, I'm probably not going to use elimination, period. Substitution is an option, but you'd have to deal with that fraction, and it's not terrible to do. But y minus x equals 2, y equals negative 1/4 x plus 7. If I wanted to do an option here, guys, honest to goodness, I'd solve by graphing. Listen, you don't even have to get this one in slope-intercept form. You can graph out of standard form by getting the intercepts. The x-intercept here is going to be negative 2, and the y-intercept is positive 2. So I can just graph those intercepts on this one, and here I can use the slope and y-intercept. Honest to goodness, graphing is the one I would actually just use on this one. One's already in slope-intercept form. The fractions had, and I don't want to use fractions for my algebraic stuff. So as long as these cross at good values, we're good. The top equation, negative 2 is the x-intercept, y equals 2 is the y-intercept there. Graphing this line, getting my arrows and colors ready. We're going to go through here to make sure it actually lines up properly, though. That is a slope point. There we go, like that. And then the bottom equation, let's just do in green. So a positive 7 here and down 1 right 4. And look at that. How about that? That's where they intersect. That is not over 4. That is over 3. Of course, I already found my solution. Up 1, left 4. And we get that. All right, my ordered pair. And remember, that's another benefit of solving by graphing. You would remember probably to write your answer as an ordered pair. Actually, well, some people just stop right here. And they're like, I graphed them. I'm good. You got to write where they intersect. But that ordered pair there is 4, 6. 4, 6. And that's the answer. Now, that is graphing. If I did use instead, however, substitution. You know what? I'm not going to use substitution. I'm sticking with graphing here. But this could take y's place. Up here, I'd probably multiply everything by 4. Get the fraction out of the way and go from there. I want to keep graphing in its main state just like that. We're good. Now, number 26. Yeah, I want to use elimination. The only thing I'm not a fan of course, are the fractions that are had. Now, I want to think about how I want to talk about this. If I multiply the top equation by 3, y's could eliminate, but that still is a fraction on bottom. So here's what I'm going to do. By default, guys, I'm already going to multiply the bottom equation by 3. I want to get rid of that fraction right down there, make this turn into 6x minus 9y equals 8. Okay, it got rid of the fraction. It did. Now I kind of have a choice on what I want to do. Would I rather multiply, and this is kind of your choice thing. 3 times negative 2 is negative 6. Y times 9 is 9 here. However, if I multiply by negative 2, that doesn't get rid of the fraction. So let's still get rid of the y's by multiplying this by 9. 9 divides by 3, right? That gets 3. So that still works out. So I'll do 27x plus 9y equals 3. That's my preferred here, and that's using elimination, as I stated. Substitution, still elimination. This is good. This is my way I'm going to go about this problem here. 27x and 6x add to 33x. These eliminate. We have 11. Okay, the answers here are fractions. X is 11 over 33, and that is 1/3. I trust my math fully on that. That's right. Look, we had fractions to begin with. I think that totally makes sense. We're going to have a fraction answer there. Let's solve for y now, and I'll use the top equation. 3x, 3 times 1/3 is good, plus y equals 1/3. 3 times 1/3 is 1. What's 1/3 minus 1? Well, negative 2/3. Y is negative 2/3. So you get 1/3 and negative 2/3. This is one where, guys, I wouldn't use graphing, period. Not just because, like, oh, the original equation things. And this is obviously in hindsight. But in hindsight, seeing that I get fraction answers, graphing would not be good to estimate where I'm actually crossing on those. So definitely not a graphing problem there. Substitution, I'm fine. Elimination is good for that. We've got to use elimination in the elimination section, and there it is. Okay. It's good we have those problems, though. And like I said, I'll link down below if I remember. I'll link down below that other pros and cons of different methods and choosing those ones and, using strategy of 12 more problems like that. Number 27 on writing. For what values of a can you solve the linear system ax plus 3y equals 2 and 4x plus 5y equals 6 by elimination without multiplying first? Explain. So they said without multiplying first, as you can tell, the y's won't eliminate through addition. And the only way for these to work out, well, the only two ways, they also state that subtraction's a way to go. And it is. I don't do it. That doesn't mean it doesn't work. So, listen, for these to eliminate, these would have to add to become 0, right? So it's either a plus 4 would have to equal 0 or a minus 4 would have to equal 0. Remember, subtraction is an option, but you have to subtract to everything. So, what can a equal? Clearly, it can be negative 4, and I'm sure you already understood that, negative 4x and 4x. Or a could equal positive 4, right? Either or would get you the additive, they'd get you valid numbers to either add down the list, boom, or subtract down the list, boom, and make it work. Through addition or subtraction, which I'm not big on the subtraction portion, but through addition or subtraction, the x terms will eliminate if a is the same or opposite of 4. Same as 4 or opposite of 4. Same as or opposite of 4. Okay. That's my reasoning. Number 28, how do you see it? The circle graph shows the results of a survey in which 50 students were asked about their favorite meal. Ooh, I don't know, man. I'm a big breakfast guy, but also I'll tell you what, I'll put lunch last, depending on lunch meals. I'll put lunch last. I love my breakfast. I love my breakfast for dinner. I love my dinner for breakfast, too. I ate a lot of leftovers. Okay, so estimate the numbers of students who chose breakfast and lunch. Well, there's less breakfast than there's lunch. If dinner is half of them is 25, then breakfast plus lunch, I'll put it this way. My breakfast plus lunch also needs to add to 25, right? And breakfast needs to be less than lunch. Maybe 10 and 15. Breakfast is 10. That's a low number to me. And lunch is about 15. Low number to me because I like it more. Just like I like rock songs more than pop and hip hop songs. But of course, that didn't really show up that way. So that's my part A. That's my estimation. That's how I see it. Is that right or wrong? I don't know. I don't care. The number of students who chose lunch was 5 more than the number of students who chose breakfast. Well, so part B, the number of students who chose lunch was 5 more than the number of students who chose breakfast. Write a system of linear equations that represents the number of system who chose breakfast and lunch. So, okay, here's one of the equations I had, and here's the other one, right? So, B plus L equals 25, and then L equals B plus 5, like that. Explain how you can solve the linear system in part B to check your answers in part A. Interestingly enough, I would actually use substitution, not elimination, because L is already isolated on this set. Although you could subtract B over and make it eliminate. You know what? It is the elimination section. Let's go back and use elimination for this. I'm going to subtract B from both sides. This becomes negative B plus L equals 5. Ignore this equation now, and now we can go to work on this. Eliminate B's. You get 2L equals 30. Divide both sides by 2, you get L equals 15. So my explanation, elimination by putting the variables on the same side of the equation. B's eliminate. All good. Now, in terms of substitution, let's do B plus L. B plus L equals 25, so B equals 10. Okay, looks like those were the answers, 15 and 10. So that does mean, if I wanted to type this thing out, 10 people most prefer breakfast. Is it students? Students. 10 students. Okay, if you ask students, I'll tell you what, I didn't become a breakfast person until college. Now, personally, I always ate leftovers growing up. I mean, cereal was a part of it to begin with, and then it was like leftovers of some sort. But once I used to have a lot of food allergies. I was allergic to eggs till about college, where I tested and grew out of my egg allergy once I hit college. And in college, I lived in the dorms. And in dorms, I had a meal plan. And as a meal plan, I got to go to the all-you-can-eat breakfast buffet, which meant omelet bar. Really had an infatuation with eggs then, waffles, things like that, even some froyo. I mean, fruit, bacon, all that kind of stuff. Really grew loving eggs or breakfast at that point. Now, why might students not prefer it as much? Because they wake up late, they jump to school, they probably don't eat breakfast, a light snack, whatever, and they don't get a full gourmet meal. So maybe once you hit college or something like that, you do it, or maybe not. Maybe you're always a late waker. So I get why their lunch is probably preferred. It's nothing to do with elimination. Let's move forward. Number 29. Your friend says that any system of equations can be solved by elimination. That any system of equations that can be solved by elimination can be solved by substitution in an equal or fewer number of steps. Is your friend correct? Explain. No. Any one that can be solved by elimination can be solved by substitution, but substitution isn't always going to be lesser steps. My friend is incorrect, especially when either, like A, let's bullet point this, either a variable already contains additive inverses. That means the 2x and negative 2x, things like that are ready to eliminate. Or isolating a variable introduces fractions in the problem. So one instance of this, and I'm going to kind of separate these to kind of show the examples. So one example set is, hey, if I already have, 2x, well, let's see, I can do them both in the same example. Let's do this. If I did something like 2x plus 3y equals 19, and listen, I don't know if this answer will be any good. Let's make it good. And 5x minus 3y equals, let's see, that's 7x, 2, something like that. Guys, this elimination here, boom, add down the list, those are gone, and 7x equals 21, x equals 3. I mean, we're done with that. Substitution? You'd have to get a variable not only by itself and isolate and all that kind of stuff, but no matter which one I do, it's going to introduce fractions everywhere. If I want to get this y by itself, I subtract 2x from both sides, divide both sides by 3, I get y equals negative 2/3 x plus 19/3. And I got to substitute that into that one right there. I mean, listen, it's multiplying by 3. It'll clear out the fractions. That's no fun. And more importantly, that's more steps. So no, this is an elimination one that is ready to go. Boom. I want to use the curly braces again. And yeah, no, your friend is incorrect in that way. Can you solve using substitution? Yes. Would I? No. All right, number 30. Thought-provoking. Write a system of linear equations that can be added to eliminate a variable or subtracted to eliminate a variable. Well, I just did one, so I'm going to copy and paste it over. I'm not going to spend more time on a problem. I don't have to. So if I can add to eliminate a variable, boom, like that, there it is. So this variable will eliminate. Y will eliminate if I add down the lists right now. I don't have anything more to say. Number 31. And maybe listen, they've done this before. Maybe the making an argument, that was the point. They want to now say, hey, show me one. And that furthers my point as far as why I copied and pasted that one. Number 31. Mathematical connections. A rectangle has a perimeter of 18 inches. A new rectangle is formed by doubling the width, W, and tripling the length, L, as shown. The new rectangle has a perimeter P of 46 inches. I need to reread that and make sense of it, because they said they doubled. Okay, so this one shows the things after you double and triple them. But there was an original rectangle with just W and L before being tripled and doubled and things like that. So before I had a rectangle with, like, I'll make this up. Let's see. I want to see if I can get the colors looking similar-esque. This might look close. Let's try this. It's too blue. Let's try this one here. It's whatever. Very solid, but it'll work. So the length was tripled from maybe this. Width was doubled from maybe that. All right, here was my original rectangle, right? So my original rectangle had a perimeter of 18 inches. And this was the width. This was the length, like that. They said, write and solve a system of linear equations to find the length and width of the original rectangle. Okay. So the original one, here's the thing. Perimeter is doubling your widths, doubling your lengths, right? So two W's plus two L's would equal our 18. That's the original. Now this one here, we double our widths. Doubling two W's, 4W. 4W plus 6L equals 46 in this case here. So this can be my system that I work off of, this and this, boom. Write and solve a system, part A, there it is. Now, I enjoy this one because I can do things to it. Here's what I'm thinking. You might say, hey, multiply the top equation by -2. Yes, but everything here is divisible by 2. I could divide these by 2. Would that help me? Not as much as actually taking the bottom equation. As much as we can multiply the top equation here by -2 to eliminate W, we could divide the bottom equation by -2 to eliminate W as well. Now, I'm bringing that up because these can also divide by 2. So that would become -2W minus 3L equals -23. Whenever I have a chance of dividing, I'm going to choose to do it. So here we go. I have these two right here. This will eliminate my W's. I get -L equals -5. Therefore, L is +5. That's 5 inches. Now we got to find the width by substituting that. So 2W plus 2 times 5. So it's once again one of those things, guys, where, you can pick and choose what to do. It's all strategy based. I'm going to work towards smaller numbers if I can. I like working that stuff out. So the length and width of the new rectangle, oh, we're not done. So 2 times 4 and 3 times 5. So width of new rectangle is 2 times 4, 8 inches. Length is 3 times 5, which is 15 inches. Let's kind of double check that as well. Remember, this is of the new. This is for the new rectangle. 8 plus 15 is 23. Doubled is 46. So yeah, that does work. Okay. That was part B. I don't know how to show where part B begins, but there it is. Number 32, critical thinking. Refer to the discussion of System 1 and System 2 on page 230. I don't know what page I'm on. Let me go back a little bit here. This was 233. So the discussion Because the coefficients of the y terms are opposites, you don't, wait, is it, oh, right here. Oh, I never saw this. Let's copy and paste this over. Hold on. I'm going to copy and paste this over. I never even saw this. Like, I didn't even mention it. I don't know what it is, so let me go back now. Okay, refer to the discussion here. Without solving, explain why the two systems shown have the same solution. Okay, so number 31. I'm going to shrink this a little bit. A little lot. Let's see what they're talking about with these systems here. A equals B, C equals D. If I add K times C and K times D to both sides, then those are equivalent because C equals D. Yeah, you know, this kind of flies into what I was talking about by why elimination method or why elimination method works the way that it does. I can add, first of all, they multiplied both sides by K right here because you can do anything to both sides of the equation. And you can add this to this side of the equation and add this to this side of the equation because they equal each other. If K times C equals K times D, then I can add K times C with A, K times D with B. As long as A equals B, then adding those are good, right? So let's see what they're saying here. Without solving, explain why the two systems shown have the same solution. The bottom equation shows x plus y equals 6 on both of them. Without solving, 3x minus 2y, 3x minus 2y equals 8. Okay, here's what I'm seeing. In the system 1, they have x plus y equals 6. If I multiply the bottom equation by 2, which is the same thing as like multiplying this bottom equation by k, right? Get the k times c equals k times d thing. Then I get 2x plus 2y equals 12, and the y's eliminate, and now you get the equation 5x equals 20. Now, we see that 5x equals 20 appears in system 2. Now, I'm not solving the rest, obviously divide by 5, but I'm not solving the rest, but I've already stated that as long as you do something to both sides of the equation that's equivalent, they belong to the same system. I even showed that once in one of the very early problems, maybe like the very first problem, that this belongs in the same system as anything else within this set because I'm doing something to the left and right side that's equivalent. I multiply both sides by 2. I added this to this side and this to this side, which are equivalent, so they all work. So my explanation is kind of vocal here, but if I eliminate the y's in system 1, I create an equation that appears in system 2 and therefore belongs to the entire system set, I guess. But they have the same solution, therefore, right? I'm working my way to my solutions with that in mind. Do I need to do something here to solve this way? No, I divide by 5 and then I do a substitution for x. But yeah, it kind of just works in that format. So I'm probably not explaining it perfectly, but the idea behind it, oh, and this is number 32, by the way. But the idea behind it is that I did rewrites. I did rewrites of things that were equivalent, multiplied both sides by 2, added the things to both sides to eliminate, and it all works out within the same system. So it's all good. I had to discover that that's where it came from, but whoop, there it is. Number 33, problem solving. You are making 6 quarts of fruit punch for a party. You have bottles of 100% fruit juice and 20% fruit juice. How many quarts of each type of juice should you mix to make 6 quarts of 80% fruit juice? Okay. You're making 6 quarts total. Let's do x equals how many quarts of number of quarts of 100% fruit juice. Let's put FJ. Fruit juice. And y is number of quarts of 20% fruit juice. I'm quoting FJ. Okay. In terms of making an equation, 6 quarts of fruit punch in total will be number of quarts of x plus number of quarts of y equals 6. The next equation gets a little weird here. You're going to make 80% fruit juice total. So here you need to mix in however much of the fruit juice of 100% with the fruit juice of the 20%, and in total you get an 80% out of that. My thought of that is 100% of x is, 100% is also 1 as the decimal equivalent, so that would be 1 times x. I mean, listen, that's the same thing as x. I'll leave it there in a second. But the 20% of y is 0.2 times y, as far as that's how much fruit juice is contained in there. And that equals 80% of fruit juice. I'm thinking you do 80% of the 6 quarts that you have. That's my guess for this system. I need to kind of think on that more as a whole. But you're taking percentages of the quarts of fruit juice to show how much fruit juice content there is. And when you mix it up, your total 6 quarts will contain 80% of it will be fruit juice, 80% of the 6 quarts. And that's where I feel your setup's going to go. So let's clean that bottom equation up a little bit, obviously the entire system. But that'll be x plus 0.2y equals, and that's 4.8. Now, personally, I don't actually want decimals with this. I'm going to work in integer form. You can multiply everything by 10. You could also multiply everything by 5. So if I multiply everything here by 5, let's just not deal. In fact, let's do this. Let's multiply by -5. If I multiply by -5 right now, this becomes a -1y, and that's a positive 1y up there. So let's just do a rewrite of these two equations. This one will say x plus y equals 6. And if I multiply this by -5, that's -5x, fine, because this is minus 0.2 times 5 is 1. So minus 1y equals, and 4.8 times 5. 24, so -24? -24. Let's see if this pans out for whatever we want. That would be negative 4x equals -18, and divided by -4, that's x equals positive 4.5. So I'm getting 4.5 quarts of the 100% fruit juice from that. At least it's a decimal, but it's a clean decimal. I anticipated a decimal, really, when you have decimal stuff here. So I'll believe it for now, but 4.5. Solving for y, x plus y equals 6, 4.5 plus y equals 6. This was, I thought this was the critical thinking question. So y is 1.5. So to me, you need 4.5 plus 1.5 is 6. And we'll see if that actually works. But how many quarts should you mix? You should mix 4.5 quarts of 100% fruit juice with 1.5 quarts of 20% fruit juice to get 80% of the 6 quarts of the whatever there. And right, that's what we're looking to do. So just as a kind of a double check, 4.5 quarts of 100% fruit juice when it's just thrown into the bowl, that's 4.5 quarts of fruit juice so far. Now you do 20% of the 1.5. What's 20% of 1.5? 0.3? Wait, is that right? Yeah, 0.3. That's 0.3 quarts of that fruit juice. It's 20% fruit juice. So if you mix 1.5 quarts of 20% fruit juice, 0.3 of those quarts will be fruit juice. The other, I don't know, what does that make it? Water? Is it diluted in water? So when you do that, 4.5 plus 0.3 is 4.8. And 4.8 is 80% of 6. So your 6 quarts has 4.8 quarts that are fruit juice, and that's 80% of it. So that looks good to me. I am feeling good on that one. Okay. Had to think about it a little bit. Number 34. A motorboat takes 40 minutes to travel 20 miles downstream. The return trip takes 60 minutes. What is the speed of the current? So 34. A motorboat takes 40 minutes to travel 20 miles downstream. So this is like a distance equals rate times time thing for me, right? Distance is rate times time. 40 minutes to travel 20 miles. 20 miles equals time is 40 times the rate of r. Is this an elimination question? So divide by 40. Your r is 0.5 minutes per mile. Minutes per mile. The return trip takes 60 minutes. What is the speed of the current? So if that's 0.5 minutes per mile, half a minute per mile, 30 seconds per mile. The return trip takes 60 minutes. Now it's the same distance. So 20 in this case equals 60 times the rate. And divide by 60 here. I just realized I'm showing the division there. Normally I wouldn't do that, but it's because of fraction reduction. I wanted to show it. R is 1/3. So 1/3 of a minute per mile. Let's change the 0.5 into 1/2 so we have agreed upon things here. So here's what I'm thinking. 1/2 minute per mile and 1/3 minute per mile. The first trip downstream. Here's the thing. The thing we don't know is the speed of the current. We still have a couple variables, not distance and rate and things like that, right? We have numbers here. The way that I'm thinking about it is this. If I take, it says, oh shoot. If I take the still water, I know what I want to write. I just want to know how to explain it. If I let x equal the speed of the boat in still water, and I let y equal the speed of the current, what happens is, because the thing is, rates can add together. They can add together, subtract together, things like that. Like if I were on a, what are these things called? You know, those moving ramp things, like at an airport, right? Those moving ramps. And let's say it was going 5 miles per hour. For some reason, it's going super fast. And I'm walking 2 miles per hour. Well, compared to someone who's just standing on the side going like, dude, you're going 7 miles per hour because you add the 5 and the 2. Maybe I should change them the other way, 2 and 5. But anyway, those things can add together. Conversely, if it was going, say, like, let's say 2 miles per hour. Now it's going 5 miles per hour the other way. You're one of those Nimrods that's walking the other direction of the ramp, something that I would totally do. Now you're going 3 miles per hour compared to somebody on the speed because you subtract them. So here's the thing. If I take the speed of the boat in still water and I add the speed of the current for downstream, this is a downstream thing. This is where my rate, and remember, these are rates. These are speeds. These are in minutes per mile. Then I get my 1/2 minute per mile. Oh, excuse me. I said minute per mile. This is miles per minute. What am I doing? Miles per minute. Distance. Boom. Miles per minute, miles per minute. I was like, wait a second. That's slower. 1/3 mile per minute. Okay. Totally screwed that part up. But anyway, x plus y. The downstream would be 1/2 mile per minute when I add the speed of the current with it because it's helping me. When it works against me, they subtract, right? The speed in a boat in still water, take away the speed of the current here, and you get 1/3 mile per minute like that. This is upstream. So that was a lot of thought to get to that stage, but now we can use, say, elimination to get there. Oh, I'm getting a scam call. It's on silent. So there it is, and I could use elimination here now. Personally, I prefer to not deal with fractions here, so I'm actually going to, and I'm still going to eliminate y. Well, they said, what's the speed of the current? So if I want to solve for y, I'd actually rather eliminate x without needing to solve for both. You know what? Let's solve for both. Let's still do it. So I am, though, going to multiply everything by 6 because I don't want fractions. So here I'm going to have 6x plus 6y equals 3 and 6x minus 6y equals 2. Now my answer might be fractions ultimately. I just don't want to deal with fractions on that one part. Y's eliminate. You get 12x equals 5 and divide by 5 you get x equals 5/12. This is 5. This was the speed of the boat in still water. You'd be traveling 5 miles per 12 minutes. Like that, which is kind of weird. To solve for y, you would now do a substitution somewhere. You know, maybe I should have just solved for y first with this thing. You know, we've done that before. So instead of using substitution, I'm going to do that, guys. I'm going to multiply the top equation by 6, the bottom equation by -6. And we'll get this down here now, where we'll get 6x plus 6y equals 3 and -6x plus 6y equals -2. And now when we get this one here, x is eliminate, you get 12y equals 1 and y equals 1/12. So that is 1/12. That is 1 minute. 1 mile. 1 mile per 12 minutes. Now, they said, what is the speed of the current? That's in miles per minute. I feel like the fraction answer is kind of weird. How about miles per hour? If this was 1 mile every 12 minutes, to convert to miles per hour, there are 60 minutes in 1 hour. Therefore, and I wonder if we should have just done miles per hour from the jump. Maybe this would have left less fractions. But minutes cancel here. You get 60 miles per 12 hours, which is 5 miles per hour. So the speed of the current is 5 miles per hour. And I suppose if I multiplied this one by 60, I would get 25 miles. The speed of the boat is 25 miles per hour. Boat speed. Yeah, I should have probably done miles per hour and stuff from the jump. I didn't realize that would be a lot better to look at than miles per minute. So either answer works here. Either 1 mile per 12 minutes or 5 miles per hour. I'm going to deal with the 5 miles per hour a little bit more. I think I prefer that one. That's going to be my approach to that problem. Okay, last one. Solve for x, y, and z in the system of equations. Explain your steps. Now, this is a system of 3. It's not only 3 equations, but it's also 3 variables. It's a critical thinking question. Now, this is where IM3 actually leans. It actually gets into more systems of 3. So the fact that they're introducing it to you now, I mean, it's critical thinking, depends on if you're assigned the question, is something that, hey, we get to play with. Now, the next equation says 3z plus x minus 2y. Guys, I'm going to rewrite this to have the x first, and then negative 2y, and then plus 3z right here. 3z equals negative 7. Just put them in order. And I'm already going to add, if you don't mind, I'm going to add the 2x over, get 2x plus 5y equals, and here you have 10. So I added the 2x over, kind of gotten them rewritten. Now, you probably don't know this yet, but in solving a system of 3, you want to turn your set into a system of 2. 2 variables, 2 equations, and solve. You can see that this third equation, equation 3, already has 2 variables, just x and y. If I can use equations 1 and 2 and manipulate them so that I get rid of z's, I'll get another system of 2. I'll get another equation with just x and y in it. So let's take the 2 equations on top, 1 and 2. Let's change the signs of equation 2. So in equation 1, I'll have x plus 7y plus 3z equals 29. Remember, I'm a preference. I prefer adding. So change the signs. Negative x plus 2y minus 3z equals positive 7. Now when I add down these lists, z's be gone. X's actually go away too. I didn't anticipate that. And you get 9y, I don't know why I didn't notice that, equals 36. My goal was to actually set up a system of 2 and solve them together, but this will still work. Divide by 9, I get y equals 4. Now take a look. Let's plug in 4 for y into that bottom equation to solve for x. And I'll get 2x plus 5 times 4 equals 10. Or 2x plus 20 equals 10. Or 2x equals negative 10. Or x equals negative 5. We still have to solve for z. And we have multiple equations to work with it up there. Let's do equation 1. We have x plus 7y plus 3z. X plus 7y plus 3z equals, they said explain your steps. I am not going to explain my steps. I'm doing them. I said them out loud. Equals 29. Negative 5 plus 28, which is 23. At least I have fraction answers I kind of feel better about them. 3z is 6, so z equals 2. Now here's the thing, guys. We talked about ordered pairs, and you don't really know things about 3-dimensional graphing and 3 variables and things like that, but this answer should be an ordered triple. Instead of x comma y, it's x comma y comma z. So my final answer should be negative 5, let's do that again, negative 5, comma 4, comma 2, x, then y, then z, negative 5, 4, and 2. Is that the only way to do it? Absolutely not. But I think that's the way that best works off elimination, getting rid of those z's. My plan, again, was to do this. Let's say that this still had an x in it. Let's say it's a 2x plus 9y, whatever, equals 36. I would have chosen this equation with this equation and continued to eliminate another variable and solved, right? And that's something that the IM3 work actually does a lot more of, but that's the one here. That's the final one, guys, and that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. We are now done with solving using all the 3 different methods that we'll look to. I actually don't know what 5-4 is, but I know that we hit 5-4 before we hit our quiz review on these things, and eventually on the other half of the chapter we hit systems of inequalities, but we got to learn a lot more about those over time. So guys, it's going to take a little bit more time to get through there. Hopefully it's making sense so far. Hopefully you've liked elimination. Of course, I think you did. And hopefully substitution and graphing still have their purposes, because pretty soon we're going to review them all. Thank you guys so much. Take care. I'm going to see you in the next one.